So should we start?
Yes, go ahead.
In a pioneering solar discovery, astronomers from the Indian Institute of Astrophysics, alongside global collaborators, have uncovered elusive miniature plasma loops in the sun's lower atmosphere. These short-lived thread-like arcs, just 3,000 to 4,000 kilometer long and under 100 kilometer wide, had remained hidden from science due to their tiny size and fleeting lifespan. However, they hold clues to one of sun's deepest mysteries, unleashes magnetic energy. Today, with this, we will uncover the unidentified secrets behind these plasma loops. I am Dr. Anubha Jain, senior journalist from ETV Bharat, and today we will speak with the lead researcher, scientist of the study, IIA's assistant professors Tanmoy Samanta and assistant professor Jayant Joshi, who are also the co-author of this research study. Welcome to our channel, sir.
Thank you.
Thank you. Yeah.
So, first of all, I like to know what initially led you and your team to suspect the presence of miniature plasma loops in the sun's lower atmosphere, and why these loops are so significant for the study. And also, these loops are just a few thousand kilometers long. So, how did your team manage to detect such fleeting and tiny features that had previously escaped, observations? Tanmay sir, can you please answer this?
Yes. So with the improvement of technology and new and better instrument, we start seeing new stuff on the sun. So in this particular observation, first time we observed some very tiny loops that we can clearly see in the sun, which are previously, unresolved, and it was hypothesized by many scientists, earlier. In this study, actually, we use different instruments at the same time, which is again uncommon for solar instrumentation because sun, solar atmosphere has different temperature, and you need multi-instrument to study different wavelength like white light, extreme UV and UV. So we need three instruments to study these loops. So for the first time, we able to use the three different instruments, one from ground, which is one of the large solar telescope in USA, and then one is the satellite, NASA satellite, which is observing in UV. Another one, again, NASA satellite, which is observing in extreme UV. So this is very exciting to study this new thing, how they are generating, what are the processes involved in the physics particularly. It's quite interesting. So that's why we started studying this.
Jain sir, would you like to add anything?
Yes. So as you asked that why it was not observed before. So I give you an example that you are sitting in a cricket stadium and you are watching a player playing. If you have a small binocular, then you might able to see the players, his face, his hand, but you might not able to see what is written on his jersey. Right, and the brand name or something, but you have a bigger binocular with the bigger objective, then it might be able to see. So what happens in the astrophysics is that the telescopes are becoming bigger and bigger, right? And you are able to resolve the smaller and smaller structures. So as the Dr. Tanmay Samanta has said, the one of the telescope used in this is the ground-based telescope from the USA, which is one of the largest telescope in the world. And using that telescope, accompanying by this space observation, we are able to resolve this very, very small structure, which are the building block of the structure of the solar corona.
Okay, right. So, what specific advantages did high-resolution H-alpha imaging bring to your study? Were you surprised by how clearly these features emerged?
Okay. So hydrogen alpha is a line which is for long term, people use this line to probe sun and solar atmosphere, the visible and it's in the visible wavelength. So it's relatively easy. But if you just look at the sun hydrogen alpha, with a filter, you will not be able to see a lot of finer details. Particularly in this study, we divide the hydrogen lines in many narrow wavelength bands, and we start observing the loop. And what we find, the loops are not visible everywhere in the hydrogen alpha line. It's only visible at particular line. And generally, hydrogen alpha line captures something cool material that's suspended on the sun. And here we see there's some strong like bright loops, in hydrogen alpha. So meaning there's some strong heating is happening in this event associated with this event with the physical process. That's why it's very interesting to study hydrogen alpha.
Okay. So you want to add, Dr. Joshi?
Yeah, I think what Dr. Samanta said is what exactly it is the in the nutshell. So as he said that because the instrument and the new instrument was made in a such a way that it able to within the hydrogen line, it's able to select the very small narrow band part of that the H alpha line, and where you're able to resolve this structure. So this is allowed by the advanced instrumentation and the advanced telescope.
Okay. So how did the use of ultraviolet and extreme ultraviolet wavelength enhance our view of these structures across the chromosphere, transition region, and corona?
Okay. So sun has defined layer. You can characterize defined layers. Particularly four layers. Photosphere, which is the surface of the sun, and then the chromosphere, which is a little bit hotter but emit invisible wavelength. Like so, we can observe the chromosphere with hydrogen alpha line. But then, if you go a little bit higher in the atmosphere, temperatures start rising to a very narrow region called transition region. Then the temperature of the solar corona is 1 million degree Kelvin. It's really a lot. And then, so when the temperature is high, the plasma emits in extreme UV, not invisible. So if you take a hydrogen alpha line, you try to see that plasma, you cannot see that. You need extreme ultraviolet filters. So extreme ultraviolet filters, in a sense, I just mentioned, emit in 1 million Kelvin temperature. So we see the loop in 1 million Kelvin temperature, meaning they are heated to 1 million degree Kelvin temperature. So that's why it's important to find out and see the loops using multi-instrument and to study the temperature, response and temperature behavior. In the beginning, we thought it's just a chromosphere loop, have a 10,000 degree Kelvin temperature, but using XPR ultraviolet, we find out, and some advanced technique when we use to analyze this event, we actually find out that the temperature is around 10 million degree Kelvin. And we discussed with Dr. Jayant Joshi, and he says it's very difficult to have a very small loop and to have a very high temperature. I think Dr. Jayant Joshi can say something about it.
Yeah. So as I said, for example, if you have is that the corona is very low density, so the gas particles are very rare, very loosely dense. But when you go closer to the solar surface, the gas density is very high. There are a lot of particles, there are a lot of atoms. So I can give you an example that if you want to distribute certain amount of money into the 10 people, and if you want to distribute into the 1,000 people, same amount of money, people will get lesser amount of money, right? With the same amount of money, if you want to distribute to the 10 people, they will get a larger amount of money. So density where it is very high in the corona, if you provide the heat would be distributed to many particles. So heating would be very low. So heating that chromosphere to the very high temperature is very difficult because you need very high energy input. But the same energy in the corona, because the number of particles are less, the atoms are less, so you can heat them to the very high temperature. So this is the biggest, basically surprising part of this study, that we find this very small, highly dense plasma loop, which are very high in the density, but they're also very hot. So this is the kind of the new results we able to find with our PhD students, who is leading in this project, which is the PhD student of Dr. Tanmoy Samanta. Her name is Anubha, and she has led this project, and we're able to find this very interesting, surprising results.
So, sir, can you walk us through the differential emission measure analysis technique and how it helped determine the plasma temperature within these loops?
Jayant, you want to go ahead?
Yeah, so it is like a probing, it's like a knowing. So for example, the solar corona has a many different temperatures. So it is not, when we say the million degree temperature, it is not that all the plasma has a million degree temperature. Some part of the portion of the plasma is also 10 million degree temperature, and some part of the plasma would be, let's say, 500,000 degree temperature. So in a very general basic way, I could say that when you do the differential emission measure, it kind of give an idea that how much part of the plasma is at the 10 million Kelvin temperature, what portion of the plasma is at the 1 million Kelvin temperature and what is the plasma. So it is give you the idea about the configuration of different temperature range of the property of the plasma. So it's able to analyze in that way.
Okay, nice.
Yeah.
So, what are the implications of detecting plasma jet, associated with the loops? Do they hint at an underlying unified mechanism behind both small and large scale solar eruptions?
Okay, the solar surface is, solar atmosphere is highly dynamic. We see very small scale jet, large scale jet. And at a time, if you look at the sun in the chromosphere, there are probably more than million to 10 million jets present at the moment, on the sun. This is very small, similar length of this.
Sir, one second. For our readers, just let me know, plasma jets, just defined in a simple term. What's this
Yeah,
plasma jet?
so it's like a narrow collimated plasma jet, just shooting up from the surface of the sun. Those are sometimes called spicule, or they have different name in terms of which wavelength we are observing. But in a simpler term, the collimated jet, like the water jet we see, like coming from something, is similar, but it's made with plasma, charged particle, and it's very common on the sun. So one of the most interesting question about the sun, how these jets are originated, and that's why, and these are again very small, similar to this loop size, from Kashmir to Kanyakumari, we say sometime. And it's important to know the process which is involved in generating this jet. And what we find that we see some jet is also there along with these loops. So they're originating together. So there is some hidden clue, that if we kind of understand the mechanism, which can explain both the loop and the jet origin at the same time, then we solve the bigger mystery.
Okay.
Jayant, you want to add something?
Yeah, and these jets are very important, as Dr. Tanmoy Samanta has said, that there could be millions and millions of jets are taking place, and there's one of the scientific fact we know in the astrophysics is that the star is losing its is some very small fraction of the mass, which is called the wind, stellar wind, and which is called the solar wind. So there is a high energetic plasma material which is flowing away from the stellar surface, or in the case of the sun, from the solar surface, and going into interplanetary medium, and then heliosphere it is going. So where this wind is coming from, the one of the answer lies, and the scientists globally suspect that this jets which are spraying out the plasma like as from the water hose, right? It is spraying out the plasma, and that same plasma is basically driving this solar wind. There's no unified consensus on this mechanism, but this is the one of the mechanism where the scientists believe that this could be driving the solar wind, which has an implication on the planetary atmosphere and the atmosphere of the Earth, and it has a wider implication on overall the whole solar system.
Okay, right.
And this study is particularly interesting. Just I want to add one thing. Here, we generally when we see a lot of nice images, right, of different astronomical objects, including sun. And when you take images, we see really nice stuff, which is moving, in any direction. A lot of reacting, CME, this thing. But here in this study, we have also used spectroscopy observation. Spectroscopy is a very particular thing that if you draw a line on the sun, you get the spectroscopic information only on that line. The velocity, the non-thermal process information, and all those things we can find out only along this line when we do spectroscopy. And we are very fortunate that in this observation, when we are taking this observation, the IRIS satellite, which is NASA satellite, was taking spectra at almost at the top of the loop, So we got a lot of extra information to interpret the generation of these loops and jet, which is extremely rare event in terms of observations.
Okay, right. These studies are involved global collaborations with NASA, MPS, and BBSO. So, how did these partnerships enhance the research and its outcomes?
So our team has very different people has different expertise. So when Anubha, who lead the observation analysis of the data, that like me, Dr. Jain, Joshi, who are expert in the kind of observation and interpretation of the data, there are some experts who are there from NASA. They are also kind of quite expert in terms of understanding the physical mechanism. So, and also we have to collaborate something with the Big Bear Solar Observatory, because this ground-based telescope obtain large amount of data and there's a lot of seeing variation. So to handle this data, we need some
So
expert
can you please repeat, Tanmoy sir?
help.
Your video was
Yeah,
hangs for a few seconds. So can you please repeat last few lines?
yeah,
Hmm.
yeah. So from Big Bear Solar Observatory, we got help to understand the basic reduction procedure of this ground-based data, which is again is a very complicated data and it's always getting affected by the seeing of the atmosphere. So we need different expert in the team to handle different aspect, and understanding the data and interpreting the result. So in that way, a global team was required to understand, because there's different instrument and different physics and different technique we are using. So different people has different responsibility, and that's how a team was required.
Okay. Jayant sir, you like to add anything?
Yeah, so this is as I said that, for example, the two space telescope and one ground-based telescope is involved, and as we know that whatever the science we started deriving, data is not recorded in the same form. The data is recorded in some basic form, which we call the raw format of the data. That data has to scientifically process. That requires a lot of computational resources, right? Sometimes you require like supercomputer to the clusters, large computer cluster to reduce this data to bring up to the level where you can start at looking and making interpretation about the data. So different expertise, different resources, all different kind of collaborations are required to conclude the result like this. And of course, the another thing is that when the collaborator institute scientists from different institute come together, when we making interpretation, we go through the many different discussions, so we derive up to the right conclusion also. Otherwise, sometime you might lead to the very narrow view about your results and the interpretation. So it is very beneficial to talk to the international collaborators and discuss your scientific results with them. So I think it is really helpful in the interpreting the data.
Okay. With India's national large solar telescope on the horizon, how do you envision the future of solar research evolving, especially in India?
Jayant, please, I think you are the right person to
Yeah,
answer.
so I can tell you. So this national large, yeah, so national large telescope, which is basically proposed solar telescope, and it would be, if it comes on the time, it would be maybe the biggest solar telescope in Asia. So I can give you an example. The current telescope which we use in our city is 1.6 meter. The primary aperture, primary mirror is 1.6 meter. But what India is proposing is the 2 meter telescope. So I could say that if you have a bigger telescope, we might be able to resolve the building blocks of the solar atmosphere, right? And we will also able to build the many developing countries in the US and the European, they have built the larger telescope, and they will going to build a large telescope. And if we want to compete in terms of this field of solar astronomy, we have required the facility which will enable our scientists to do the cutting edge research. And this is the one of the very essential requirement for the advancement of the solar physics, heliospheric physics. And as you know that the sun is very important factor on how the atmosphere, the magnetism, everything is shaped in the solar system. It has implication on earth environment and everything. So studying the sun is very important. We require our own telescopes to understand what are the processes taking place on the sun, what are the fundamental physics, understanding the plasma physics, its interaction with the magnetic field, but as well as some implication on the life on the earth actually. So we require this kind of national facility, and if it's come on time, I think there would be a very good advancement of the solar astronomy in India.
Right. And in the end, just want to ask what's next for you and your team, the next line of research work.
Yeah, Dr. Tanmoy, Samanta,
Yeah,
maybe.
so this is just the beginning. This is when we study something, we find something new, and then we started investigating of this small scale phenomena. We open up new windows of research. It's not the end of the research, because we will be able to see. I think now it's the most interesting thing we are seeing. we'll be able to study more and more. And with the upcoming facilities, now we are target will be to study those events, in more details. So future will propose in many observations using multi-instrument, telescopes to observe this kind of phenomena in details and try to find out in more details how the magnetic field stored the energy, how the energy is converted to heat and the kinetic energy in terms of jet. And that will give a lot of insight in the physics happening on the sun, and also it will add to like kind of the space weather research information, because the solar winds are basically coming from the small scale phenomena. So in that terms, so there's a lot of things to be done, and we're excited to carry forward this research, and future is
Right, sir.
right.
Jayant, sir,
Yeah, that's
would you
what I
like to
feel.
add any of your concluding note?
Yeah, definitely. As Dr. Samanta said, that when we discovered something, we found new results. It is giving you some new discovery or the new answer. But with this new answer, there are thousands of new questions also raised from these new discoveries. For example, we are able to found this miniature loop, but now we want to know if this miniature loop is very common on the solar surface or it is just very few. So we really want to know the implication on the larger context of the shaping and the structuring of the solar atmosphere, what kind of the role these small scale loops play in terms of the solar structure dynamics and their evolution. So there are many new questions has raised from this study, and we would like to, with our collaborators and we have many PhD students in this institute, and they will be now working on those new ideas and then answering to these new questions coming out of this recent work, actually.
Right, sir. Right. Thank you so much for this insightful information. Thanks a lot.
Thank you.
Thank you very much.